Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Let's proceed with more thermodynamics today. Today we will cover the first law of thermodynamics and the problem with the first law. Then we'll see how second law can be helpful in that regard. To start understanding that, we'll start with certain foundations. That is a relation between CV and CP. We will see. And then what is reversible and irreversible processes. To understand the first law of thermodynamics, let's start with this system. It's in state 1. What happens if we heat it? It slowly expands and reaches a different state. The gas inside is getting hotter and the volume expands. Okay, what happened here is we have supplied some heat Q, and this Q has been converted to two different energies. One is, if you see, the gas is now hotter and the temperature goes up, then we can then in the last class we saw that internal energy goes up, right? When temperature goes up, internal energy changes, and here there is a mechanical work of lifting the weight on top of the piston, right? So the Q that we have supplied has become increase in internal energy and a mechanical work. That is those are the changes. There is a work done which is equal to P delta V. The pressure is constant P. Delta V is the volume change. So work can be directly calculated like that. Then there is an internal energy change, which is nothing but increase in the kinetic energy of particle constituents. The Q that we have supplied is now splitted into these two parts, W and delta U. Therefore, the heat is converted into two other forms of energy. One is the mechanical work and the other is change in internal energy. So in this process, energy is conserved. There is no energy created or destroyed. Only a form of energy is converted to other forms of energy. Right? The classical conservation law of conservation of energy is the first law of thermodynamics. What first law implies is that any process that conserves energy can happen. For example, all energy available on Earth, except nuclear and volcanic energy, comes from the sun through empty space by radiation. Or it came in previous geological eras and was stored as coal, mineral oil, or natural gas. Basically, meaning that any energy comes from the sun is taken into the plants by photosynthesis. If they are dead plants, they convert into this kind of coal or mineral oil, natural gas, and so on. The plants which are alive are the ones which are driving now all the biological system. They are that's the place where the entire energy storage starts from the sun and it flows through all the living beings. The problem with the first law is this: Q equals W plus delta U, but the opposite is also permitted. What if the gas which was actually expanded gets compressed naturally and releasing heat? Okay, that can happen, right? So minus Q is equal to minus W plus delta U can happen, meaning this reverse process. Since the energy is conserved, this is permitted. Can that happen naturally? So intuitively, you know that the gas cannot naturally get compressed and then release the heat from the bottom. It doesn't happen, right? But since energy is conserved, yeah, there is amount of increase in internal energy, right? That increase is now reversed, and there is a mechanical work done by the system on the surrounding, and now that is also reversed. Then what happens? These two energies become the heat Q and go out of the system. Okay, and in this entire process, this equality will hold minus Q, because the direction is reversed. We are putting minus. That's all. Okay, essentially we are telling that W plus delta U is equal to Q. Okay, So since this equality holds, the energy is not created nor not destroyed, and one form of energy is getting converted to the other form of energy. So simply this reverse is also permitted by first law of thermodynamics. That's the problem. Okay. So it means that sun's energy flows through the plants to all the animals in this direction, but the opposite also is true. From our from animals body, energy can be taken to plants, and plants can send the energy back to the sun. Because energy is conserved, this can happen. So first law permits processes that take all the energy back to the sun as long as the energy is conserved. So that's the problem. So first law is a fundamental law of universe. According to that, which processes are permitted in nature? Any process that conserves energy, and any direction is permitted. This is the problem with the first law. So this any direction is permitted, which is the problem with the first law, is addressed by the second law. We will now start to see how to understand the second law. We have to lay some foundation to go about understanding second law. Okay, we will start with few of the ideas. The first one is going to be relation between Cv and Cp. Consider 1 mole of ideal gas. Cv is amount of heat required to raise the temperature by 1 degree, and since volume is constant, we are putting this. So according to first law, we saw that del Q, meaning in the differential form it is written now, del Q is equal to du plus pdv. Okay, this is the work, this is the change in internal energy, and this is the heat supplied, right? Since volume is constant for the Cv, we will remove this pdv part. So all the heat supplied is going to only changing the internal energy. So Cv, this del Q we will replace with du. We have in the last class seen that U is equal to 3 by 2 RT. Of course, a small n RT we saw because we are taking 1 mole of ideal gas, that n we have removed. This is going to be dou by dou T of 3 by 2 RT. If you do the differentiation with respect to T, you will get 3 by 2 R. This is a simple relation, a simple value for Cv. It's like a constant, right? 3 by 2 multiplied by a constant, that is the Cv of ideal gas, right? Now what about Cp? Cp is del Q by del T at constant pressure. Again, take the first law, substitute instead of del Q, du plus pdv. Okay, so here instead of du, we are writing 3 by 2 RT. pdv is there, so we are writing pdv by dt. So this dt goes to the denominator in both the sides. We can take this p and put it into this differentiation part, dou pv. Since it's a constant, this is not a problem. Since we see this pv, we will replace that pv with rt. Okay. That's the only change we are doing here. So if we do the differentiation now, what are we going to get? We are going to get 3 by 2 r from the first term, just in the case of Cv, plus from this part we are getting one r. Okay, therefore 5 by 2 r. This is also a constant. Cp is also a constant for ideal gas, 5 by 2 r, which is nothing but Cv plus r. So Cp and Cv are connected like this. We can also write Cp by Cv is 5 by 3 or a constant gamma. And this is going to be a useful relation as we go forward. So this is a relation between Cv and Cp. This is one idea. Then we will see about reversible and irreversible process, a very important idea to understand the nature. Okay, let's consider two cases. In both the cases, there is some gas inside and some mass is kept on the top in both the sides. Here the mass is in some chunky form. Here it is some small stones form. Okay, but the total weight here and here is same. The total mass is same here and here. Then we are going to remove the 1/3 of mass from here and here. We will see the gas is going to expand to a same final state. Okay? But in these two cases, the path is going to be different. That's what we are concerned about currently. Okay? Two cases of expansion between the same states, meaning the initial and final states will be same in both the cases. The initial, more specifically, the initial and final load on the top of the piston is same. Okay? So let's see how to do that. We are going to remove 1/3 of the weight now. In the case 1, we are removing 1/3 in single step so that expansion happens quickly, and this is the final state. In case 2, we are going to do stone by stone removal. Therefore, the expansion is going to be extremely slow, and eventually it reaches a state where the weight on top is only 2/3 now, 1/3 is gone. So instead of these stones going out, if we have taken initially some kind of a sand heap and remove sand particles one by one, it's going to look like that. Okay. If you do it by removing sand particle one by one, it's going to be even extremely slow process. So in this process, there is something fundamental going on. Okay? The amount of work done in this case is actually more compared to this case. Work in the sense of moving the mast up, that work is more in this case. We are going to understand how it has happened. So let's see one by one. Okay, let's take the two cases again. Consider both the previous processes only after step 1. Okay, take only the step 1. After step 1, in case 1, the system goes from the initial to final state directly. Whereas in case 2, after step 1, there is barely any movement. Okay, we can't even perceive it. This is what happens when you remove one small stone. Now put that small stone, small grain, back on the piston in both. Only the grain on both. Okay, so put the grain back here. Does it go back to original state? No. We are not putting the entire chunk back. We are only putting the grain back. In this side also, if we put the grain back, what happens? We can say it has gone back to the original state, right? Of course, we can't see the movement, but we can perceive that it would have gone back to the original state. So we have done a small change in the surrounding. We have put the grain back. By that, we see whether the system goes back to the original state or not. Okay, case 1 does not go back to the original state, this side, whereas case 2 does. So that's why we call this case 2 as reversible and case 1 as irreversible. So what is a reversible process? Reversible process is when a process happens, system and surrounding change, but do only a tiny change, a infinitesimal change in the surrounding to reverse the process. The target here is to reverse the process. In that intention, a small change is done in the surrounding. Therefore, we see whether the system and surrounding go back to original state. If yes, then the original process is reversible. If not, it is not reversible. It's called irreversible. There can be some misconception here. So people tend to think that reversible means there is a cyclical process. Reversible process is a cyclic process. Answer is no. Reversible process is not a cyclic process. And this is a source of confusion. Okay. Reversible process, is it same as cyclic process? Answer is no. Reversible process does not refer to a cycle. What it means is this. It refers to a process that go only in one direction, but it should have the character of coming back to the previous state with a tiny reversal. Okay. The surrounding you do a tiny change. In the surrounding you do a tiny change, the system goes back to the original state. That process is called as reversible process. It's not the entire cycle. Is the process, forward process, has the ability to come back with a tiny reversal in the surrounding. That is called as reversible. Okay. Now let's consider these irreversible processes. All of them can do different levels of work. It is quite interesting. If you see, there is some mass here on top of them. Same mass in all the three cases. Only thing is they are split into 2 parts here and 3 parts here. Okay. If we do removal of this mass from the top, The entire mass goes out here, one half goes out here, and one third of the mass goes out here. Then the expansions happen like this. In which of this case more work is done? In this case, the piston moves without any load on top. Here it moves at least half of the load. Here it moves 2/3 of the load. Obviously, more work is done in this case, right? This is an important idea to keep in mind. Also, the velocity is developed. If you see, the velocity of the piston was quite rapid in this case, and it gradually came down as we go to the right as we go in the right direction. Look, all three of them together, you will appreciate the velocities. Okay. This is the fastest, this is the slowest. What if we go towards even slower, even smaller kind of chunks? Okay, here at least three pieces were there, one piece is removed. The case that we saw previously, here also we are going to remove that 1/3 of mass, but we are removing it grain by grain, so that you can see the velocity is extremely slow already. Instead of this kind of grains here, if we take a small sand particles like this, would any velocity develop in such a case? Okay, barely you will see any velocity developing. Barely any velocity. You remove a grain weight, you barely see any movement. Those kind of processes are called reversible processes. You put the grain back, it will go to the original state. If you put a grain back here, nothing will happen. It will not go back to the original state. Okay, so the reversible processes are almost like they stay in equilibrium all the time. Whereas in this removal of chunk, once you remove the chunk, the system is not in any equilibrium state. It is in a highly transition state. It goes from the one state to the other state quite rapidly. So during that movement, it is definitely not in equilibrium state. Whereas when we remove sand grain by sand grain, we know that at each step, the system is attaining some kind of an equilibrium. Okay. So those kind of processes, that achieving equilibrium at every step, those kind of processes are called reversible processes. Okay. So as we go along, we will be looking at representation of these different states in PV space. What is a PV space? We will spend a minute and see. We actually saw that in the internal energy case in the previous lecture. So today we will spend a minute on this and see what is that. Okay. So this is an initial state. It has some volume, pressure and temperature. This is a PVT space, and this dot here is representing this state, pressure, volume and temperature corresponding to this state. Now, if you think about this line here, what does it mean? It means that the pressure value is constant, the temperature is constant, but volume is increasing. Is that possible? Because system has to, like all these different states, are they possible? If it is an ideal gas, then these all other states will not be possible, because PV equals RT. If it is 1 mole of ideal gas, the system will follow this equation of state. These are the states which can be called as equilibrium states. So if you think about different volumes without changing pressure and temperature, it is not possible. If you increase the volume and want to keep the temperature constant, your pressure has to come down, right? So if this equation has to be followed, all these different states cannot be called as equilibrium states. Okay, they are not possible to be achieved. So this PVT space represents all equilibrium states. Now think about system going from one state to the other state. Pressure decreased, new volume and temperature achieved. This point can be represented here. Okay. So now these states will be represented directly into the PV space. Don't think that temperature is 0 here. It is just a projection to PV space. Okay, so temperature is not 0 here. You know how to calculate the temperature. If it's an ideal gas, if P and V have a certain value, then according to this equation, T is going to be dependent on that. So only representing PV is enough to understand indirectly what is temperature. Okay, so this space, PV space, is what we will be using as we move forward. So PV space shows only equilibrium states. So when you remove the load, initially the system is not in equilibrium, it is in a transition state. That state, what we don't know what is the pressure and all, because pressure is not going to be uniform everywhere, okay, inside the gas. So once it is achieving the equilibrium, once it achieves the equilibrium, then we know what is the kind of pressure throughout the system. That can be called as an equilibrium state, can be represented in this space. Okay, so this space is only representing equilibrium states. That is important. Now let's bring back that irreversible process of expanding the gas by removing 1/3 of the weight. Let's put it in the PV space and see how to understand that, and we can calculate the work done in this process. Okay, so remove 1/3 of the weight. What is the new state? We can figure out. It's going to have different volume, pressure and temperature. We'll put this P2 V2 point here. That is the new state. Right. Now, what happened here is it's not following the equilibrium path. Okay, it's not following in the reversible path. So we don't know what is the pressure initially, but this yellow line can be put as an approximate path for this process. Meaning initially pressure drops, right? The moment weight is removed from the top, pressure initially drops from P1 to P2. You can say that. And against this P2 pressure, expansion of volume is done from V1 to V2. Then what is the work done in this process? Since it is an irreversible process, we are going to put this subscript IRR. So W irreversible is the work done by the gas, which is the area under this curve. Nothing but pressure into delta V. P delta V is here. This is the pressure against which this volume change V1 to V2 has happened. So P2 multiplied by delta V is V2 minus V1. That is the work done. Nothing but the area under this curve, this rectangle here, right? So this, once it is removed, the pressure immediately drops here. Remember that, okay? And against this lower pressure, the entire expansion is done. Therefore, there is only a smaller amount of load that is lifted by the gas. Keep that in mind. Lower amount of mass, in the sense, there is if the mass is removed grain by grain, then there would have been more mass to lift, at least in the initial stages. You can imagine that. Okay. So the process where we removed the material grain by grain, since it, by removing this grain by grain, the system is in some kind of a static state at every step. We can call it quasi-static process. That is a better name, because reversible in a very strict theoretical sense means the system is already under equilibrium. If things are already under equilibrium, why do they move? Okay. So practically speaking, a quasi-static process can be considered as reversible process. Okay. So here again, initial state is given P1 V1. Then the material is removed grain by grain. It reaches to final state P2 V2 is the final state here. But how to calculate the work done here? When the first step, one grain was removed, pressure dropped here. Okay, volume changed, pressure and volume expanded to this point. From this point, volume expanded to this point, pressure dropped from this point to this point. So if this particular volume change and pressure change will happen for removal of every grain, so that the system achieves these different states. Okay. Instead of this stone, if we go for a small grain kind of thing, then these steps would be much smaller and much more closely packed, and it will look almost like the system covers all the pixels in this line, isn't it? So that is called a reversible process, a reversible path. System is in equilibrium at every step of it, and it will follow this P equals nRT by V equation. In the reversible case, how to calculate the work? W reversible, work done by the gas. When the first step happened, it's almost like the irreversible process, but to only a tiny extent. So we can draw this kind of a path for this. And what is the area below that? That's going to be some pressure into some volume change, P delta V, PdV. So that is here. So if we do that for every step, these different rectangles we have to add up. Okay. Instead, if we go for very tiny grains of sand grains removal kind of thing, we may get even smaller rectangles like this, and eventually the area under this entire curve we can get if we approach the ultimate reversibility. And this area under the curve can be calculated by integration PdV, and nothing but the equation of this curve. We know that for P, by rearranging P equals nRT by V, that is the equation of this line. Okay, we can take that and integrate it with respect to V, so we get the W reversible. You can see this is quite high, isn't it? Initially, work done by the gas is higher than the irreversible case. In the irreversible case, we saw only up to this much, right? Like this much. W irreversible is only this much. So this much extra work can be extracted in reversible case. Okay, so this much work is lost in the case of irreversible process. A related idea is called exergy. Exergy is nothing but the maximum possible work from a system, which is nothing but the work done in the reversible process. So if at all a process is done reversibly, the system can give out maximum possible work. And this much work only is possible if we do it in the reversible way. So therefore, this maximum possible work has a special name called exergy. In the irreversible process, what happens is exergy destruction happens, meaning the maximum possible work is not possible to be obtained. There will be some destruction in that. Okay. In future, we will do this as entropy production. Okay. These are two sides of same coin: exergy destruction and entropy production. People who bothered about making engines more efficient and things like that, they may be bothered more on how to conserve or how to extract out maximum possible work from the system. Whereas when we apply all these thermodynamic ideas to materials and chemistry and understand them, we will see that any process that happens in nature actually produces entropy. Natural processes are invariably going to be irreversible in nature. You will realize that. And they are all going to be having some kind of exergy destruction, meaning they will all produce some entropy. Okay, we will see about that in future. So when we talk about a cycle of reversible and irreversible processes, not just one way, we will go and come back totally in the reversible manner and irreversible manner. So this is an expansion. Now consider the reverse, that is compression, where work will be done on the gas. So we'll come back from this second state to the final state again in multiple steps. If we make the steps tinier and tinier, we will eventually achieve this kind of work which is done on the system. Okay, this is the reversible compression. Okay. So work done in the forward case is equal to negative of work done in backward case. That is how the reversible process work. In the irreversible process, if you do the compression, expansion we saw, when we do the compression, gas gets compressed like this. Then from P2 V2 state, we come to P1 V1 state in one single step like this. But you can see the work done here is actually very high. This is not exactly true. We may not come to this exact point. We will see that there is some change to this in when we cover things like adiabatic processes in future. But you can imagine one thing, the work done here is definitely high. There is more area under this curve. That is the work done on the gas. So if you want to compress something in an irreversible manner, you have to do more work. Okay, in the previous case, expansion case, we saw that in the irreversible expansion, we saw that there is less amount of work extracted from the system. The work done by the gas is lesser. Whereas if you want to compress the gas in irreversible manner, you have to spend more work compared to how much work you spent in the reversible case. Okay, this is the amount of work required in the reversible case. So there is some more amount of work required in order to compress the gas in an irreversible manner. Okay, work done on the gas is higher than in the reversible case. Okay, and forward and backward work is not the same. In the forward direction of irreversible process, only this much of work is done. In the irreversible case, this much extra work has to be done to achieve the compression. And this is an important summary. In reversible process, W forward is equal to negative of W backward, whereas in irreversible case, These two are not same. So this is all about the system. What about the surrounding? We'll see about that in the next class. I hope the lecture is useful. We'll see in the next class.